In this video lesson, we are going to go through the solutions to the homework exercise that was set at the end of the previous lesson. And if you can recall, in the previous lesson, we were looking at the use of conservation of charge, baryon number, and lepton number to predict possible interactions. And so this is what we are going to do in this particular video lesson. At the end of the previous video lesson, I assigned the following exercise for you to do, and that was asking whether the following particle interactions were viable based on the conservation laws that are necessary for a particle interaction to be viable. We're now going to look at the solutions to each of these four interactions. So in this interaction, a proton is converted into a neutron plus a positron plus an electron neutrino. Now, looking at the charge, we see that the proton has a positive 1 charge, the neutron has a 0 charge, as does the electron neutrino, but the positron has a +1 charge, and so we see that it's +1 on the left-hand side, +1 on the right-hand side, and therefore charge is conserved. When we look at the baryon number, or the baryon number, we see that the proton has a +1 because it's a baryon, the neutron has a +1 because it's a baryon, but both the positron and the electron neutrino, they are leptons, and so therefore they have a 0 baryon number. And so here too we can see that the left-hand side is +1, the right-hand side is +1, so here the baryon number is also conserved. When we look at the lepton number for each of these, we see that the proton has a 0 lepton number because it's a baryon. The neutron is a baryon, so it has a lepton number of 0. The positron has a lepton number of -1, and that's because it's the antiparticle to the electron, which has a lepton number of +1. And we can see this in the table. If we go to the table here and we look at the lepton numbers, we see here for the electron, the lepton number is +1, and so for the positron, the lepton number would be -1. You would be given a table like this in your information sheet in tests and exams. So when we now look at the lepton number, the muon electron, not the muon electron, the electron neutrino has a lepton number of +1, and we can look and see in the table, if we go to the electron neutrino, we see that it has a lepton number of +1. It's the anti-electron neutrino would have a lepton number of -1. So when we now go and look at the total lepton number on the left and the right hand side, we see here too it is conserved. So this proposed interaction is viable as it satisfies the conservation laws of charge, the baryon number, and the lepton number. So this is a viable interaction, and this is an interaction which actually takes place in the real world, and we'll learn more about this later on in this course. In this interaction, a muon is proposed to change into an electron, an anti-electron neutrino, plus a muon neutrino. So looking at the charge, we see that the muon has a -1 charge, the electron has a -1 charge, and the neutrinos and antineutrinos have a 0 charge, and therefore we can see that charge is conserved because the left-hand side is -1 and the right-hand side is -1. When it comes to the baryon number, none of these particles are baryons. They are all leptons, and so therefore they all have a 0 baryon number, and therefore it's 0 equals 0. The baryon number is conserved. When we look at the lepton number, all of these particles are leptons. So if we look at the muon, it has a lepton number of +1, so the muon has a lepton number of +1. The electron has a lepton number of +1. The anti-electron neutrino has a lepton number of -1, and the muon neutrino has a lepton number of +1. And we can verify this if we look in the table here. We see here is the information about leptons, and if we look here, we see there's the muon. The muon has a lepton number of +1. We have the muon neutrino, which has a lepton number of +1, and if we look at the look at the other one that we need, and that would be the anti-electron neutrino. So if we look at the anti-electron neutrino here, we see that it has a lepton number of -1. So therefore, we see then when we add up everything on the right hand side, we get +1 -1 +1 gives us +1. So the lepton number is also conserved. So therefore this interaction is also viable, as it satisfies the conservation laws of charge, the baryon number, and the lepton number. So let's consider this interaction. In this interaction we have a tau negative particle changing over into a muon plus a anti-muon neutrino plus a tau neutrino. Now, from a charge perspective, the tau negative has a -1 charge. Tau negative is basically a heavy electron. The muon has a -1 charge, and the antineutrinos and neutrinos have a 0 charge. You obviously can pick this up from the table on the right. So on the left-hand side, the total charge is -1. On the right-hand side, -1. So here, charge is conserved. None of these particles are baryons. So if their baryon numbers will all be 0, and therefore the baryon number on either side is 0. So the baryon number is conserved. They are all leptons. And so the tau negative has a +1 lepton number, and the muon has a +1 lepton number as well. The anti-neutrino, muon neutrino, has a -1, and the tau neutrino has a +1 lepton number, and so therefore we see +1 equals +1, and so therefore the lepton number is also conserved. So this interaction is also viable, as it satisfies the three conservation laws. So now let's move on to the last question. So here we're looking at uranium-238 decaying into what we'll learn about later on as an alpha particle plus a thorium-234 atom. So if we now do an analysis of the protons, neutrons, and electrons in each of these complex particles, so these are not fundamental particles, these are not elementary particles, these are atoms, so, and nuclei, and they've got nuclei that consist of protons and neutrons, and there are electrons as well in each of these atoms. So if we look here, we see immediately, if we look at uranium, and you can do this, you did this, should have done this in grade 10, where you take the atomic number, which is the smaller of the two numbers of the element on the periodic table. Now we've got 92, 2, and 90. You take the neutrons are determined by the mass number subtracted minus the atomic number, or subtracting the atomic number from the mass number. So 238 minus 92 gives us 146. In the case of the helium, this is in actual fact a helium nucleus, because it's lost its 2 electrons, therefore it's plus 2. You see the number of neutrons is 2. Here we have neutrons, number of neutrons is 234, minus 90 is 144. So now if we look here, we see that the charge plus 92, because protons are plus 92, the electrons is minus 92, that gives us 0. So this is a neutral atom. On the right hand side we have plus 2, because that's the charge of the nucleus, because this is 0 electrons, plus 90, because it's 90 protons, minus 90, because electrons is 90 of them and they are negative. So we get 0 does not equal 2. So here the charge is not conserved. So we can see, well, okay, this is problematic. If we go to the baryon number and we add up all the baryons, we see here, adding up the baryons is the protons plus the neutrons, and each of these has a baryon number, each proton and neutron has a baryon number of plus 1. So we've got 92 times plus 1 is 92, 146 times plus 1 is 146. Yeah, we've got 2 protons, 2 neutrons in the helium nucleus. We've got 90 protons in the thorium nucleus, and we've got 144 neutrons in the thorium nucleus. So adding up, we're 238 equals 238. So the baryon number is conserved. When we go and look at the lepton number, now the leptons here are what we can see at this point is we can only see the electrons. And so we get 92 electrons on the left. We get 0 electrons in the helium nucleus, and we get 90 in the thorium. 92 does not equal 90, so the lepton number is not conserved. So this interaction is not viable as we see it at present, because it violates the conservation laws of charge and the lepton number. But when we encounter phenomena in physics that seems to break the rule or does not seem to fit particular conservation laws, and yet we know that that process actually exists, and that process is actually alpha decay from a U238, which we know actually exists, we then need to look deeper. And this is one of the beauties of science, is that in essence, science is never ending. One can continue to look on deeper and deeper and deeper levels into phenomena, and in doing so, one gains a deeper and more beautiful insight into nature. So looking here, the decay of U238 is a series of decays. These transmutations taking place. We'll learn more about this later on in the course. So step number 1 is where the uranium-238 decays into the alpha particle plus the thorium atom as we saw it there. Now, the second step in the series is that the thorium decays into a palladium, into a beta particle, which in actual fact is a high energy electron, and an anti-electron neutrino. Right, so this is in actual fact beta decay. Now beta decay we'll learn about more later on, but in beta decay we have a neutron that changes into a proton plus a beta particle, which is the electron, plus the electron antineutrino. So this is one of the three main radioactive decays. You get alpha, beta, and gamma. Then the palladium that is formed here, that daughter nucleus, so this would be a daughter nucleus of the uranium, as with this. This daughter nucleus then beta decays, producing another daughter nucleus. This daughter nucleus then now decays into U234. Now notice how the mass number has decreased, but it's still uranium. There's another beta particle and there's another electron neutrino. So there's two beta decays in step 2 and step number 3. So if we now go and look at all three of these processes, and we now look at the charge, we see that we actually get that the charge is conserved. So we started off with a neutral atom. We produced an alpha particle, which is +2, and 2 negative electrons, or beta particles. And so 0 equals 0, which implies that the charge is conserved. Charge cannot disappear. It's not something that can just disappear into the ether, as it were. So we have to be able to account for it. Now, when we look at the baryon number, we started with 238, we have 234, and we have 234 on the left-hand side. On the right-hand side, if we look on the right-hand side, we have 4, we have 234, we have 234, we have 234. So we have them here. So when we add that all up, we get 706 on the left-hand side, 706 on the right-hand side, and the baryon number is conserved. If we now go and look at the lepton numbers, we see we've got 92. Remember, this is not only the number of protons, but also the number of electrons. So it's 92, 90, and 91. On this side here, we don't have electrons in there. We have 90, we have 91, we have a beta particle, which is an electron, so it's +1. An anti-electron neutrino, being an antineutrino, it's going to have a lepton number of -1. We have 92 for the 92 electrons in that uranium, +1 because it's a beta particle, -1 because it's an electron neutrino, and voila, we get that the lepton number is also conserved. So albeit that from the method that we're using, that the first step, which is what we were presented with, did not seem viable because not all of the conservation laws were met. When we see that it as a series, in other words, that it's part of a greater whole, and that there were another 2 processes that followed, then we can see that all 3 of these are viable, and this is in actual fact what happens in reality, and we will learn more about this later on in this particular course.